Here we go. 10C, 10D, stationary points. Stationary points occur when again? Do you guys remember? What's a stationary point? When gradient equals 0. But to find the gradient, you
find the 0 except for the derivative.
The derivative. So hence, it occurs when delta y delta x equals 0 or f dash of x equals to 0. Okay, so it's when the gradient equals 0, but remember the derivative at a single point is the gradient of a tangent line. So this means stationary point is the, what's that? See where the gradient of the tangent line at the point is 0. I think that's meant to be the, what's C? Coordinate. I wanted you to remember the coordinate because when they ask for stationary point, it's not just the x value. You have to give it in terms of x and y in brackets. Okay, so when you're finding it, find the x, and then you've got to find the y coordinate to it as well. All right, stationary points. So in this diagram here, we can tell from exercise 9D, you now know when it's positive, when it's negative gradient. We can tell that on this side, all gradients are positive. Then it reaches point A, gradient 0. From A to point B, we can tell that the gradient is now negative. Until you get to point B, again, 0. Similarly, from B to C is also continuing to be negative gradient. So negative, 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 negative. And then you get to 0 at C. And then it's positive again from C. That means that a stationary point does not tell you if you have a local maximum, a local minimum, or an inflection point. Because at point A, B, and C, they all have the same gradient of 0. So when you say delta y delta x equals 0, you're not saying that it is a maximum. You're not proving anything. So when they ask you to justify that the stationary point is a maximum, you can't just say delta y delta x equals 0, therefore it is a maximum. You actually have to show that. One of the ways we show it is through a sign diagram, which is what you see below here, where you actually test out the value. So you would have found the derivative at what x value to get a gradient of 0. You have to sub in that value to show that the shape of the sign is a horizontal line gradient 0. But then how do you prove its local max? You literally have to pick a point. So you might say -1 or 1, and you actually have to find the gradient value. You can't just do plus and a minus. Okay, so if it's a justified question, you actually have to sub in what derivative at x equals -1 is, and what is the derivative at x equals 1 is. Then you can say, yes, this is positive, this is negative, therefore you get a local maximum. Okay, assuming that the gradient is positive on the left and negative on the right. So that means the same thing for your local minimum. Local minimum occurs when the gradient is negative first, then 0, and then a positive gradient. Whilst an inflection point maintains either positive, positive, or negative, negative. Right? And we talked about the inflection point being that concavity, and that change in point where it changes either its increase in rate or decrease in rate. Okay? Let's do an example. This is question 7 of exercise 10C. So you've got the gist. We now know stationary points occur when the derivative equals 0. Derivative equals 0 does not tell you the type. You need to use some justification if they ask you to justify. But let's look at this question here. The curve with equation y equals ax plus b over 2x minus 1 has a stationary point at 2, 7. What that's telling me is that it says the derivative is equal to 0 at when? Delta y delta x will equal to 0 at, very good, at x equals 2. Okay, so they gave you a point, but remember it's the x coordinate that we're looking at in terms of derivatives. So at x equals 2 is the key coordinate that we're looking for. Okay, then they say find the values of a and b. Well, one of the first informations we got is that we can find delta y delta x Let's go. Who's game enough to have a derivative go of ax plus b over 2x minus 1? Who wants to have a go? What's the derivative? Ryan.
A plus 2b and then 2x minus 1 brackets 2 over 2.
I'll say that again.
2b on the outside.
2b on the outside.
Then 2x minus 1 on the inside to negative 2.
To negative 2. All right, let's do this. So 2x minus 1 all to the negative 1, okay, times by, I think there should be a negative at the front. Oh, but then did you find the derivative inside?
That's the chain rule.
Yeah, I think there might just, I think it's a negative at the front. For those who aren't doing it in their heads, let's take our time to write it out again. So y equals ax. What Ryan is doing is he's pulling the denominator to become 2x minus 1 all to the power of negative 1. That's what he's doing there. And then we're finding the derivative of each component. Derivative of ax, well, really it's derivative of x. That's why we know it is just a, so hence delta y. Delta x gives us a, so the derivative of ax gives us a. The second one, yes, it is a chain rule. Derive the inside. So remember, derive the inside first. The derivative of 2x minus 1 gives me 2. And that's why Ryan said here, that's going to be 2 times, and there's a b, that's a constant. So b times, and now you have to pretend that doesn't exist, and it's something to the power of negative 1. So u to the power of negative 1, think of it that way. Think of u to the power of negative 1. If I ask you what's the derivative of u to the power of negative 1, you would then say it's negative 1, bring the power down. So bring the power down, minus the power by 1. So it should be 2x minus 1 minus 2. Yeah? So I'm just doing that as a quick chain rule. If those who are sort of confused there, you probably have to write it properly, let it equal u, and do the chain rule. But ideally, you want to get to the point where you can do it by inspection. Okay? So by inspection, yes, it is all mostly correct. It was just that minus that we got to be careful of there. But yes, this is our derivative. What's the next bit? I'm just going to write it with the fraction above. So it's 2b over 2x minus 1 squared. Okay, I've just brought that 2x to the power of negative 2 all the way down. All right. We said that the stationary point occurs when the derivative equals 0 at x equals 2. So that means at x equals 2, so that means if I sub 2 into this equation, the derivative, which is delta y delta x, should equal 0. So that means my equation should be 0 is equal to a minus 2b over 2 times 2 minus 1 squared. So far, so good? No questions? Let's evaluate. This gives me a minus 2b over 2 times 2 is 4, 4 take away 1 is 3, 3 squared gives me 9. Another way of thinking about it is if you don't like that fraction, times all the terms by 9, and you get 0 equals 9a minus 2b. That's equation 1. Because likely, if you've got 2 unknowns, you're going to need 2 equations to simultaneously solve this problem. I got 1 equation, and all I used was the derivative. I used the stationary point has to equal to 0 for the derivative. That's what I got. What do you do now? What do you do now? So I'm going to zoom out just so you can look at the question again. So I used the first piece of information. Stationary point occurs at 2, 7. I found the derivative, which is over there. I showed you the chain rule, what Ryan did in his head to get to the derivative. Subbed in x equals 2 and the derivative equals 0, and I've got 1 equation. Have to solve for A and have to solve for B. So where's my next piece of information?
You sub 2.7 to the original equation.
Beautiful. And that was hidden. So that's usually a typical exam 1 question, probably the first or second one, where that 2, 7 is essentially telling you when x is 2, y is 7. So we now then can say that point when x is 2, y is 7. Well, the original equation was y equals a times x plus b over 2 times x minus 1. That's in terms of x and y's, not derivatives. So then you sub the 7 into the y and sub 2 into the x. That's how you're going to get your second equation. All right, here we go. Let's write out my second equation. So I've got now 7 is equal to 2a plus b over 2 times 2 is 4. 4 take away 1 is 3. And by the same concept, if you don't like the fractions, times every term by the denominator. So right now it's divide by 3. So if I times them all by 3, then I should now get 21 equals 6a plus b. And that's my second equation. Much easier to work with than keeping the fractions. Simultaneous these two now. So from this point, it should be more directive or more self-explanatory. Most of you should be able to then solve this part now. Let's put it all together. I'm just going to write in purple on this side just to make a bit of space. I'm trying to work out 0 equals 9a minus 2b, and you've got 21 equals 6a plus b. How do we solve this? Elimination method or substitution method? Up to you, doesn't matter. I prefer elimination method. So I probably would have just changed that b. The b is the easiest one to, in my mind, to rearrange. I'll probably just times them all by 2. So times this by 2, times this by 2, times this by 2. That gives me now 42. I'll just rewrite it again. That's now 42 equals to 12a plus 2b. It's equation 1. This is my new equation 2. And I would then do a subtraction or addition. So minus 2b plus 2b should give me 0 of those b's. 9a plus 12a. So if I add these two equations together, 9a plus 12a is, what's that? 21a? 42. Therefore, a must equal to 42 divided by 21, which is 2. Has anyone done it ahead of time and got a equals 2 as well? All right, very good. Therefore, solving for b, if I just sub it back in, so 0 equals to 9 times 2 minus 2 times b. What's that? 18 equals 2b, and b must equal to 9. Is that correct? All right, sweet. Coordinates of the other stationary point. Ooh. What are they talking about here? 2, 7. Were we meant to have 2? Well, I'm confused. What happened? Oh, because now we've got A and B. Ah, what a pain. I must have thought it was just a substitution. Here we go. Let's do B. The coordinates of the other stationary points. So we now know that the derivative, sorry, A and B, we now know A and B. A is 2. So derivative delta y delta x is equal to 2 minus 2 times 9 over 2x minus 1 squared. Is that right? So really your derivative is equal to 2 minus 18 over 2x minus 1 squared. That's your delta y delta x. To find stationary points, it's when delta y delta x equals to 0. Solving for this. But didn't we solve it already? No, we didn't. All right. Solving for this, we will now move the 2 across. Minus 2 but then it's a minus 18 over 2x minus 1 squared. So times both sides by negative. You can just probably rub this negative off. Get rid of the denominator, times both sides by 2x minus 1 squared. We get now 2 bracket 2x minus 1 all squared is equal to 18. Divide both sides by 2 again. Gets you 2x minus 1 squared is equal to 9. Alright, this is not too bad, actually. What do we do afterwards? What do we do now? Square root both sides. And when you square root both sides, what you have to be careful of. Very good. So that means square root of 9 is plus minus 3 now. So we get 2 possible answers there. Plus minus 3. Add 1 on both sides. So that you get plus minus 3 plus 1. And finally, your x-coordinate of your stationary point could either be plus minus 3 plus 1 divided by 2. So the two solutions are, if you had 3, it'd be 3 plus 1 is 4. 4 divided by 2 is 2. Or negative 3 plus 1 is negative 2 divided by 2 is negative 1. All right. And which one do they give us? 2, 7. So we already have this one. We now found the other coordinate is negative 1, y. And that's our next stationary point. To find the y coordinate, what do you do? Beautiful. Sub it back into the original. Oh man, so much space I'm running out here. What's that? Y equals to 2 times negative 1 plus b, which was 9, divided by 2 times negative 1 minus 1. Is that right? Yeah. What does that give me? Negative 2 plus 9 over negative 2 minus 1 is negative 3. Negative 2 minus 3. Oh, beautiful. Works out a bit nicer. Did you guys get the same answer as me? Oh, you went ahead already. Beautiful. All right. Sorry, team. I will fix my notes there and give you much more space than what was actually there. Probably could have taken a full page there. All right. Wonder if we were meant to use a CAS or not. All right, team. That was the first, well, it's question 7 of exercise 10C, but it's the next two that I'm interested in. Flip over the next page. I want you to have a go with answering this. Now, I gave you the picture to what the derivative of x squared e to the x looks like. So you can technically answer it from looking at the graph, but I also want you to do it algebraically. How would you have done it algebraically to get the answer as well? The last one gets you thinking a bit, and I'll help you towards the end of that one. But I'll give you guys about, let's go, it's 46. Let's make it 10 minutes. And remind me if I'm going off track, so I'll come back to give you the solutions to this one, okay? Let's pause the video there. All right, let's check your answers here. So you found the derivative using product rule, vu dash plus uv dash. We got this. Next step is, usually in the exam, you should try to find any common factors to factorize. In this case, I only took out the e to the x. But normally in the exam, you take out the x as well, yeah? I took out the e to the x because it separates it as an exponential function and I got a quadratic function. I did that because we're finding the derivative. When is the derivative less than 0? By separating the two, I can essentially ask, well, when will e to the x be less than 0? Or when would x squared plus 2x be less than 0? One of the things we know is that e to the x cannot be less than 0. It's always above the x-axis. So then it just leaves us with x squared plus 2x. When is that less than 0? We can sketch that graph. And that looks x-intercept negative 2 and 0. We can see it's less than 0 between negative 2 and 0. Hands up if you got this as your answer. Beautiful. Alternatively, if you did have a graph, then we can see this is the derivative graph. When is the derivative less than 0? It is clearly between negative 2 and 0 in that graph there. Okay, but if you didn't have a graph, then there's a couple of things you can play around with the algebra there. The second question, 10D question 14 says sketch this graph here. Y-intercept, we know let x equal to 0. So if I let it equal to 0, it's 1 over 1 equals 1. So we all should have the point 0, 1. Then the x-intercept let y equal to 0. One of the first things you should pick up here is that will be undefined. Or if you multiply both sides, 0 does not equal to 1. Doesn't make sense. Or you can think of it as 1 divided by something. Every time you do 1 divided by something, it can never equal to 0. Okay, so hence, that tells me I should have an asymptote on y equals 0. So you should never touch the x-axis. Hands up if you've got at least those two properties there. All right, very good. And then the analysis comes in. So most of you should be able to pick up on this with a bit of analysis. What is, as x approaches infinity, so if I go towards the right, we should see that as the value or the power, if this gets infinitely large, so 1 over a very large number, you can think of it as if you had one pizza and you are sharing it amongst the world's population, you're getting very, very little of the pizza. Okay, so hence it should be approaching 0 because you're getting very, very little. So both sides, if you tried that out, whether it's negative infinity or positive infinity, both should be 0. Hands up if you got that. Okay, good. Good analysis. The next bit you could probably still get if you just subbed in 0 on both sides as it approaches 0 because it's not undefined or anything. So you can technically do limit of the function 1 on e to the power of 0 squared on 2 really approaches 1 on e to the 0, which is 1 on 1. So did you get 1 for both ends? Yes? Okay. The other little note there that I thought, so some of the confusion should be around the idea, does it go infinitely as you get closer to 0? Does it go infinitely up? And why does it approach 1? One of the properties that might be helpful for you as a general fact, if you did the nth root, so the power of anything, right? So 1 over whatever it is, no matter what that number is, if the number is greater than 1, it will approach 1, but it will just be slightly above 1. Okay, so here's an example. If I did, 1.1111 to the power of, 1 on 999, right? You see it is approaching 1, so the nth root will approach 1, but it's slightly bigger than 1. But if I change that base value, and I said it was 0.91, then it's approaching 1 as well, but it's just slightly less than 1. And I just thought that could be a useful fact for you to know when you're working with nth roots and you're working with limits. That could be a nice thing to know. And because we know that 1 to the power of anything should be 1. So then what happens if you have just a bit above and just a bit below? So hence in our case it was e. It was e to the power of x squared, negative x squared on 2. We know that the closer it gets to 0, regardless, it's the same idea. It's the power of something infinitely close will still approach 1, but except it's very, very, just a bit above 1. That's it. That's usually the idea if the value is above 1. But there you go. This is what the graph should look like. If we draw it correctly, we should get something that looks like that. Well, let me do it again. Terrible graph there with all that little shakes there, but how do we go? Did we get something like this? It kind of looks like a little mountain cap. Yeah. All right. That's it for today's lesson. So that's 10D. 10D's analysis of the types of stationary points along with the derivatives, whereas C was working with stationary points. Okay. All right, team, I'm going to stop the video there.